So in the following demos, we will have a deeper look at the startup process for the STM32F4 controller. And in the process, we will actually see how the startup GCC file initializes the processor, and we will have a look at the interrupt vector table and see the entire process of startup in the debugger. Now, before we go there is something interesting that I need to show you. We are in the folder for our makefile linker, and we had gone through the lesson on makefiles. Now, whatever object file you see here are not created by the actual makefile here. That is run by the IDE. So I ran this command separately. So if you remember, we had a discussion stating that the commands that we had in the primitive makefiles actually build the files in stages, but the final makefile did not do that, but it took care of the entire timestamp control of the input files. So we are going by one of these makefiles. So thus I had obtained the .o files and the .out file here. So please do not get confused here as to from where I got these files. But again, though I advise against it, this folder is being shared between my IDE and commands that I'm going to issue right now. But anyway, let's proceed and let's see a few things. So we will first look at the startup gcc.o file. Okay. We will do an obj dump for the startup gcc.o, and we will have a look at the section where the interrupt vector table is laid out. So let us do that. So arm none and then to display all the sections, we do a dash capital D, and then we do a dash S and dash X, and then we give the file name, that is startup underscore GCC. Okay. And let's make it full screen and get the dump. Now we are only interested in having a look at the vector table. So can you see the vector table here? The funny part is nothing of this is resolved yet. Not funny exactly, but this is how it is. That's the process. The interesting part, I should say, the interesting part is none of this is processed here. So all the function calls that we saw previously in the interrupt vector section are all unresolved. So it is the job of the linker, or during the linking stage, all of this is going to be resolved also, which is something that we did not discuss in the previous sections. So now we see this, that is, it is not resolved. We have different function calls, we have the default handler, we have the sysdig handler. That's it. Addresses have not come in yet. Now if we want to, now let's see the output. So let's clear the screen, and now let's see the output. So if we see the output, that is, we will go and check the build example.out, and it will become clear to us. Let's go and check up the interrupt vector section here. Now, if you see the interrupt vector section now, you'll see that it has all been resolved now. Okay. Let us do one thing. Let us drop one option here. This looks too cluttered. Let us drop one option and check out the interrupt vector section. So we'll not have the -d option now, because this will only give us the interrupt vector table for the final file. So if we have a look at it, we see something, that is the vectors have all been resolved now. That is, whatever we saw was unresolved previously, addresses have been put. Now there is something interesting here. Now this is the first address, and you have to read it in this direction actually. Okay, from right to left. So because it is starting from lowest to highest here, so it is 20000410. So this is the initial stack pointer address. Okay, so this is what the and this has been done by the linker. So yeah, this is interesting. So the initial stack pointer address has been put as we expect it to be. Okay, and this has been picked up, and so the link, whatever we had put in the linker script file, and then it saw the particular array that we had declared for the stack, that is 256 long words, 256 words, that is unsigned long or unsigned int, and it has put the address of the top of the stack here. That is okay. Now if you see this is the address of the reset handler, because the address of the reset handler has to be put next. If you remember, if you see the interrupt vector table, the address of the reset handler has to be put in next. Now let us see what the address of the reset handler is in the map file. So we have the output map, and let's go and check the reset handler, reset ISR. So it is 8000198. That is the address of the reset handler. And you can also double check it in your map file. Your map file might look different, but this one and this one is going to be, should be the same value, but we see that instead of 80000198, we see a 99 here. Now ARM Cortex-M4 has to have the last bit in the vector table set to 1 if to indicate that this is in the thumb mode. And that is the reason, don't get confused when you see these addresses. If you see that it's one higher, and it might look it's out of alignment and so on, but that is not the case. The fact is that we are here even at the linking stage, this correction is being done. Okay, so this is quite, it's a quite clever manipulation that is done by the linker, so again the second function. Okay, the second function is, if you look at the startup file, first function, the second function is your NMISR, fault ISR, int default handler. All these functions are going to have 1 in their least significant bit, indicating that it's a thumb operation, and that you don't have to do it. It is automatically done in the linking stage. So I hope that is clear to you. So this is something that is extremely important, and I had to clear it out before I move further. There's a clever mechanism in which this is actually figured out, and when the instruction actually starts for the reset ISR, then the correction stops. That is, you don't anymore do that correction. The correction only happens in the vector table. Okay, I have not seen the correction happen anywhere else, to the best of my knowledge. Now that's one point that I had to clear up before I get into the actual demo. Now let us come back to the startup file and check out how this whole process works of setting up the vector table, so on and so forth. For that, when you are doing it on your end, you have to set a breakpoint here, by double clicking here or here, and you need to set up a breakpoint here and also set up a breakpoint in the call to main. Now generally you'll see that the control will go and stop at main if you don't set any breakpoint in the startup. So what we have done here is I've set a breakpoint in main so that when I start the debug session, it comes and halts in this function because there is a lot to show here. And we went through this file. We know about eText, data, eData, BSS, EBSS, and so on. So this is going to get really interesting. So now you have the reset ISR function, and we talked about these variables, that is PULSRC and PULDEST, and these variables, since it's declared within the function, it should be somewhere on the stack, though the stack has not yet been readied, but nevertheless it is going to use the stack anyway. So the first part, so let us put it on debug first and then check out a few things. So we have the control come and stop here. Now if you look at the linker script file, we need to have this data section which is in the flash move to the RAM. That's the first job we do, and second job is to zero out the BSS section. So we spoke about that. Now we'll see how it actually happens in action. Now what is the PULSRC value? So it should be the value that is pointed to by eText. So it will not yet have the value. Let us step one further, and then PULSRC is going to have the value of the point from where the data stored in the flash starts, that is 8008800574 hex, if you can see. So this is 800574 hex. Now let us have a look at the memory. Now we will have a look at the memory from the beginning itself, that is from where the flash starts, and we will go down and we'll try to see what is where. Now let's bring it up a bit. So this one, the first one, is the stack address 2000410. That's the top of the stack pointer. Okay, and let's see if this value coincides with what we saw in the objdump output. So 2004010, see 2000420000410. So let's see what we have here. 20000410. So here you don't have the one added, it's just the plain top of stack. Then from here the interrupt vector table starts. So 8000198, that is the actual address for the reset handler, but we have it as 199. Then 800204, so it will be 204 if you look at the just a moment, I'm not sure if this is come here. Okay, those functions are declared as static, so you will not see those function names in the map. We did discuss this. Static values, we discussed it for a variable, but then statics will not show up in the output. So if you declare this as non-static, then you will see the function names here. So these are the function names function addresses, and 8000211 is the address of, and that is the occurrence of that is the maximum here, and that is the address of this, that is the int default handler, and the address is actually 8000210, but this one has been added to compensate for the, because it is for thumb. And the interrupt vector table goes on till, so let's take the pen now. So it goes on till here. If you see, it goes on till here. This is where the vector table ends. And here the text section starts, that is the instruction start here. The code starts from here. It's once the exception vector table ends, so this is where it ends, and the code starts from this location. Now, so this is the dot text section. If we go down, so the dot text section continues. So if you need to verify that this is indeed the code, what you can do is we will have a look at the output file now. So once we see the output file, it will be in the .out file. If you see, after 800194, address 800194, from 800198, so this is 4 bytes, so 800198, the instructions start, and the instructions are thumb instructions, 2 byte, B580, B082. So let's have a look at this. If you can see, it is B082, B580. So LSB, MSB. So this is how the instructions proceed. Okay. B580, B082, and it goes on like this. So this is all the instructions for all the 3 files, because it's all the text section has been brought together, right? So you have a complete code here. So after the code section, we'll have the data starting. So that is the data that we are looking at now. So this one, so this is where the code ends, and you have the constant data also here. That is the RO data, that is the data that is declared as constant, is mentioned here. That is, you have these constant values, right? test1 and test2, 100 and 999999. So let's see if we can find test1 and test2. So that is going to be after the code section. So we'll have to go to the map file and see in the RO data section, we have it in 8000056C and 8000570. So here are the 2 positions where we should find the test1 and test2 variables. So let's try to find them out. So 8000056C. So 56C. So 8000056C has this value 000064. So what is 64? So it is test1, 80056C. So 64 is actually 100. 64 in hex is 100. So we have one variable here. Now the next one is, if you see the map file, next one is test2, and it is in 800570. So this is 56C and this is 570. Now this value, okay, so the value is F423F. Let's open the calculator and see what value is F423F hexadecimal. So F423F, and as expected, that is the value is 999,999, and that's the value that we have here in the build example main. So this is in the flash section. Okay, now this is from where the data that is supposed to be copied over to the RAM resides. So what is this data? This part. Okay. So let's do one thing. Let's now step into the code, and actually this section, that is your underscore data, or not underscore data, e-text is going to point to this address location. What is this address location? We'll have e-text pointing to 8000574. Okay, so e-text points to this address location because the data ends here. That is the RO data ends here. The text section ends here. That is your code. Now this is where it starts. We know this by seeing the code, but seeing the memory layout. But let us see it in the code as well. That'll be fun. So what we do is we have set the breakpoints already. Now let us restart it. It is good for debug, so let us restart it again. So now this is on debug. Now underscore e-text is, we need to see what is the value of underscore e-text now. So if we go down just one step, just do a step over, ULL-SRC or underscore e-text is 08000574. Do you remember we saw 8000574 in the memory browser? So 8000574 is the address where the initialized variable data is placed, not constant data. We saw that just now, and we saw that the address is 8000574, but we are seeing that in a different fashion now. All right, so let's go to that memory location, 8000574. Now 8000574 first has this address. Now what is this address? Now this is the address of &_BSS section. Okay. So this is the BSS section address. Again, look at the linker file. This is where the BSS, we have to zero out the BSS section, right? So this is the address of the BSS section, and that is what we are seeing here. That address has been stored because we had declared a global variable here, and we discussed why we needed to put it there. So when we do the copy from the flash to the RAM for the data, this data is also going to get copied over, and this section of the code is going to use the data that is already copied over to the RAM for its purpose. So if you had tried to run this now, that part of the RAM is going to have a junk value. So we know that. So let us investigate the data that we have here. So let's see, what do we have? We talked about this. Now we have 1 here. Now this 1 is being contributed by this value. Not main, sorry. We'll go and check this out. Explorer, if you core initialization, this one, okay, this value in core initialization has and since it's a static value, you will not see it in the output map file, okay, but this one is being, this one is the contribution of this particular variable, static variable. this one, and it is not in the stack because it's a static, so that is why it is here. Now we have two more values, that is 10 is 16 and C is 12. Now 16 and 12, so let us see what are those values. So let's go to the data section, and we have EP2 polling rate and test 0, and here you have the address as 2008 and 200C, because this shows where the data actually should go into, but EP2 and test 0 are here, that is in the flash, that is it is 10 is 16 and C is 12. Can you see this? So we have a segment of data that is here. This is 4 word, I wouldn't say 4 words, but this whole block will get copied into the RAM now. It is not yet copied. It is not yet copied. It will be getting copied into the RAM now. So let us open a new tab, and here let us do a, so where are we copying it? So let's see. So if you really need to know where we are copying it also, let's do a single step again for the value to come in. So we do a single step, and this is the destination, and destination is 2 with 7 zeros. Of course, this is the beginning of the RAM, and the beginning of the RAM is underscore data. So you can verify it in multiple ways. Okay, so beginning of the RAM is underscore data. So what we'll do here is we are going to check the RAM address now. So here you have some junk data over which the RAM is going to copy what we saw from the flash. So let us step through this and see how the data gets copied. So let us do a step over. So let us press F6. Keep pressing F6 and see what happens. And since this is a byte copy, it will copy in bytes. So pull dest into pull src. So you see we get 10 coming here first, because it is going to copy. Now it is after 4 steps, because this is a byte copy. You have this value coming to the RAM. So flash, from the flash 80574, it is coming to the RAM. Okay. So this is how. So if you keep stepping through, so let's keep stepping through. The value will not change immediately because we are doing a byte copy. Okay. Now see, this value has gone to 1. So 2 words copied, but number of steps here are more because we are copying byte by byte. Okay. So from here, it's copied to here. Let's proceed. Third word, 16 has been copied. So we are left with copying 12. So let's see. So it came out of that loop because it had copied 12. So this value. So now if you see the 12 that you had, okay, it only copied 1 byte because and it left the rest because we only need this much. So this one and this one, the 12, it will look different now. 1, 10, and then it's like 0C only. It leaves the rest as it is. So that is what. Okay. Now we see that all the 4 words, not 4 words, but whatever data we had to copy, we have already copied in the memory. This region is actually freed up. This people can actually write stuff here. So we have occupied up to here actually 0C, that is 2000F, that is 20000F. Never mind how many zeros I said, but I meant 6 zeros. All right. So now we come into the zeroing out of the BSS section. So let's see what the BSS section address is. So it is 200000010. Okay. So let's go to the BSS section. So where does the BSS section start from now? Let's see. So this is where the BSS section is starting from, because this is where your data section ends. This is where the BSS section starts from. Now we will run one iteration here, and then we will just run till this breakpoint, and we will see something happen here. Okay, so let's run one iteration and show you what happens. If you notice here, this section has been made into 0, okay, because of this loop, and it has done it in bytes, because again this is happening in bytes. So if we give it a free run now, and it'll come and hit this breakpoint now, and let's see what happens. Did you see? All this has become 0. So the entire BSS section has been made 0. So, and what is the EBSS value? Now let's see. DST less than EBSS. The DST will be 2BB4 now. DST value is 2BB4. If you want to check out what is the end of this value, DST, that is the last value, this is 2BB4, that is the end of BSS section. So let's go and check up 2BB4 now, and 2BB4. So just till then you have it all zeroed out. So 2BB4, as we know, is the one address higher than that, right? So this is one. This is the end of the BSS section, and that is the end of the initialization for the startup file that we have here. And then next step, it is going to jump to main. That is it is going to be a call to the main. So if you see the disassembly now, it is BL 8000510. So let's see, 8000510 is the address of the main function. So let's see the output map. Let's hope that we have the main somewhere. Just a moment. Yeah, here you have the main 8000510. So this is where it jumps to next. So I hope you followed how the startup file works. So more or less, this is the mechanism by which all startup files are going to work. That is for ARM Cortex-M at least. But this is the basic concept. So if you understand this concept, you will not have any problems in writing startup files by yourself.